Okay, our next speaker is Hemamala Karunadasa, and I believe she's in her second year as an assistant professor in the chemistry department here at Stanford, and her entire research group develops perovskite materials for various applications, and today she'll talk about her GCEP project on using them for solar cells.
Great. Thank you, Mike, for the introduction, and thanks also to Sally and Richard for the invitation to speak. I'm really thrilled to be here today to tell you a little bit about our very recent results in hybrid perovskite solar cells. So this is a collaboration between my group in chemistry and Mike McGee's group in material science and engineering. And we are a bunch of synthetic inorganic chemists, and together with Mike's group in engineering, we both synthesize new materials that could function as solar cell absorbers, and we also test these materials in actual devices. So to start, I want to I'd like to start with the structure of this material and try to explain to you why there's so much excitement about hybrid perovskites in the photovoltaics community. So perovskites are a huge family of compounds, and these materials have been known for many, many years. In fact, the first work on perovskites dates back to the 1800s. And you can form perovskites with metal oxides, metal sulfides, metal halides. And these materials have very versatile electronic structures as well. So you can form perovskites that are high band gap insulators, semiconductors, conductors, even high temperature superconductors. These materials are everywhere, and these properties of perovskites have been exploited for many decades. And these materials have this, the same general overall structure. Here I show you the structure of this lead halide perovskite material that has caused so much excitement in the photovoltaics community, where the inorganic framework just consists of a very simple framework of lead halide octahedra that share corners. And this extends out in all three dimensions, and this framework has a net negative charge. So therefore, to provide charge balance, we need very small positive ions that have to reside within the cavities of this structure. So within each cavity that's defined by 8 corner-sharing octahedra sits a very small organic cation. Well, it can be either an organic or an inorganic cation. In the case where we put a very small organic cation, like this methyl ammonium that I've just shown as a gray sphere, these materials are called hybrid perovskites. But there are many related materials which can be structurally derived from this overall structure. So today I will talk to you about both this 3D structure shown here, as well as a family member, which is the 2D material. And you can again think of the 2D material as if you took your 3D perovskite and took a very fine knife and started slicing layers of your 3D structure. And again, you get this an extended two-dimensional array of corner-sharing lead-iodide octahedra, but now you have this additional advantage at least for structural tunability, which is that between these sheets you can put much larger and potentially more elaborate organic cations. And later in the talk, I'll tell you why you might want to work with both the 3D as well as the 2D structures. So one thing that continues to amaze me about these materials is that they form on their own accord. This is called solution state self-assembly, which means you can just take a beaker, put it on your bench, and just throw into solution your precursor ions. So you can throw in the halides and the metals and the organic cations. And if you just tune your conditions just right, these materials form on their own. And the beauty of self-assembly is that whenever you get molecules or ions to do what they want to do, they do it perfectly well. So when you get to the conditions just right, you can isolate these hybrid perovskites as crystalline powders, thin films, and in my group, we love to grow single crystals because they are beautiful, and also because you can do very precise measurements on well-formed single-phase single crystals. In fact, every picture I show you is from a single crystal X-ray diffraction study. So I want to discuss some of the strengths of this material. There are many. I'll just highlight some of the points that I think are worth mentioning. A very important point about perovskite absorbers is that these materials can be formed through solution state methods, which makes everything extremely inexpensive. The precursors are very cheap, and you can use solution state methods like spin coating, drop casting, or vapor conversion methods to make these materials. So here I show you a schematic of one particular way to make nice films of hybrid perovskites, where we can simply take a mesoporous titania scaffold and drop a solution of lead iodide into this material. The solution will coat the scaffold and form this nice layer of lead iodide. Lead iodide forms a layered structure, which means that it likes to form uniform films around any kind of scaffold. And lead iodide is yellow, so we get this yellow film. We can then simply take this film and immerse it into a solution containing methylammonium iodide, and the methylammonium iodide will work its way in through the lead iodide film and convert that film into the perovskite. So our yellow film is turned black, and we are left with this beautiful uniform film of the perovskite. We simply heat this film, drive out any volatiles, and we're left with a nice film that we can then continue to fabricate the solar cell device. So that makes everything very cheap and very scalable. I think this is the chart that I stole from Mike's slides that gets everyone really excited about these materials. There's been a very, very sharp increase in the efficiencies of these materials over a remarkably short period of time. So the first solar cell, as Mike mentioned, the paper came out in 2009, and this was a really neat result, but it kind of stood alone, and it was more of a scientific curiosity. And then in just a very short time, these efficiencies got to the point where everybody cared very deeply about these materials. And there's certainly no sign of plateauing, so we can most likely expect further increases in the efficiencies of these materials. 2009 was a very memorable year for me. I was writing my PhD thesis when the first paper came out, and I just read this paper and thought, oh, that's neat. But then by the time I started my group in 2012, things got a lot more exciting. And this was a great, great subject to work on. So I'll tell you some of the reasons why these materials have these great efficiencies. It's very remarkable that these materials have very intrinsic properties in its photoexcited state. So when we hit these materials with light and we create photogenerated electrons and holes, these charge carriers can move around very freely. The diffusion lengths are very long, and they don't recombine very easily, which means we get ourselves some time for those holes and electrons to go their own separate ways and complete the external circuit in the solar cell device. And these materials seem remarkably tolerant of defects. In fact, you don't need beautiful single crystals of these materials to realize very high charge carrier mobilities. Even polycrystalline powders behave very well, and even films, which is very strange and very unusual for solar cell absorbers. And this is the typical diagram we show when we talk about the energy levels of a solar cell absorber in contact with charge carriers. So the basic idea behind a solar cell is that we have a semiconductor. This is your absorber, so in this case, this would be the perovskite. And we hit this material with light corresponding to this band gap energy. And the idea is that we excite an electron from the filled valence band shown here to the empty conduction band shown here. We now need to separate those electrons and holes and send them their separate ways. To do that, we need materials that can conduct the electrons and conduct the holes. So the way that we can move this electron to electron transport material is to drop it in energy. And the way we can move these holes is to raise it in energy. Holes, that's just an absence of an electron, so raising the energy of the hole stabilizes it. So by necessity, this diagram shows nicely that the voltage you can get from a solar cell is smaller than the band gap of the absorber, because just to be able to transport those carriers, we had to drop the energy of the electrons or increase the energy of the holes. But some very interesting recent reports have shown that these perovskites are not just great absorbers, but they can also transport charge very well. So imagine getting rid of this electron conductor. In this case, your absorber is both the absorber and the electron conductor, which means you just bought yourself a lot more voltage, a lot more obtainable voltage. So this has been shown for both electrons and for holes. So perovskites are really versatile materials. And a very nice attribute of these materials is, again, just through solution state self-assembly, we can start adding different ions into the lattice. So we can start with the lead iodide lattice and then start doping it with bromide, and we can change the absorption energy of the material. And you can see that there's this nice increase in band gap as we start adding bromide into the lead iodide lattice. And being able to tune the band gap of the material is very interesting for lots of applications. With respect to solar cells, Mike mentioned that his group works on tandem devices, and they have indeed shown that tandems can work very well. In a two-absorber tandem device, the higher absorber the band gap of the higher energy absorber has to be about 1.9 eV. So with lead iodide alone, we get a band gap of about 1.5 eV. So in order to get to 1.9 eV, one potential strategy is to incorporate bromide into this structure. I'll get back to whether we can do this or not, but the fact that we can tune the band gap is very exciting for applications as solar cell absorbers, light-emitting diodes, and lasers. It's very cool to think that we can simply change the structure and change the color of the light that comes out of this material in a laser. So these are, I hope I've convinced you that these perovskites have very promising properties, and I love perovskites. I'm a huge advocate of these materials, and I very much want to see this technology work. But precisely for these reasons, we've decided to focus on the weaknesses of this material, because we want to identify any problems that we might find in these materials so that we have a chance of addressing them and hopefully resolving them. So for the rest of my talk, I will focus on the weaknesses, the potential problems that we might encounter using these materials. There's no denying the fact that there's lead in this material, and a lot of it. There's a lot of concern that this lead is not just toxic, but these materials are water soluble. And there are many people who say, we've just removed the lead from our houses. Are we really going to coat our roofs with lead back again? So this might boil down to just an encapsulation problem. But for now, there is some concern about the toxicity of the lead, particularly a water-soluble source of lead. Another problem that we have seen in our labs, we've seen this firsthand, is that these materials are not stable to moisture. So we can form nice uniform black films of this material, and here's a nice annealed film of the 3D perovskite, and if you just let it sit on the lab, on a bench in the lab, over the course of a few days, I hope you can see this, there are these yellow patches that start forming on the surface of your film. So it's bad news when your black solar cell absorber turns yellow. That means it's not absorbing sunlight. So these yellow patches are lead iodide patches that form. This material converts to lead iodide in ambient moisture. In fact, you can see this even more clearly in the absorption spectrum. This is the band gap of your perovskite, and over time, you see that this band gap decreases, and there's this higher energy band gap material that forms. This shows that the perovskite material is decomposing, and lead iodide is forming instead. And the final point I want to bring up is something that has become more apparent recently. I told you that by adding bromide into this lead iodide lattice, we can change the band gap. So we can form materials that have a band gap of 1.6 using a lead iodide lattice, as well as a material with a band gap of 2.3 EV using a lead bromide lattice. And by using intermediate stoichiometries of lead and bromide, we can actually access all intermediate band gaps. But when we look at the voltages that have been achieved using these materials, the lowest band gap material gives a low voltage, the highest band gap material gives a high voltage, but the intermediate band gap materials do not give higher voltages than the lead iodide material, and this is very curious. So we decided to investigate why this might be as well. So we have efforts in both our groups to address all 3 points, but for the rest of the talk, I will focus on the last 2 points and show you our efforts on trying to make a more moisture-resistant material, a lead perovskite with greater resistance to moisture. And I'll also talk to you about our investigations on why these mixed halide materials don't deliver the high voltages that we expected them to give us. So I show you again the picture of the 3-dimensional perovskite. It's a beautiful structure, but for a synthetic chemist trying to make a material modification, this can also be a very frustrating structure because there isn't much we can do. So if we want to maintain the beautiful absorption properties of this inorganic framework, we really don't want to mess with the inorganic structure. So that leaves us with only these very small organic groups to play with. This cavity really restricts the size of the molecules that can enter this structure. So if we want to improve the moisture stability, we could swap out this cation for another small cation, but there isn't much we can do. We wanted more space. So we took a step back and looked at some related materials that we had been studying before we moved on to 3D perovskites. So in my lab, prior to our work on solar cells, we had been working on the layered perovskites that I showed you in one of my first few slides. So these materials have just one inorganic sheet sandwiched by organic layers above and below, and this is a repeating unit. And I'm going to call this n = 1. This has a very large band gap, and this has very high exciton binding energies, which means when you hit this with light and you generate electrons and holes, these charge carriers are very strongly attracted to each other. In fact, these have all the properties that you seek to avoid in a solar cell absorber. And we know that these materials have other advantages. We've found that some materials which have these n=1 sheets are actually very nice phosphors. So when we hit this material with blue light or with UV light, the material emits white light, broadband white light, which looks like sunlight. And we know that the reason you get this emission is because this layered material gives rise to electronic structures, which induce very strong exciton binding energies, as well as very localized charge carriers. And we know that if we were to simply expand the thickness of this inorganic sheet all the way to n=infinity, we know that we can decrease the band gap, and we know that we can also decrease the exciton binding energy. And we also know that these two are extremes in what's really the continuum of the hybrid perovskite family, so we decided to make the intermediate species. And you can see that there's this nice change in the electronic structure as we go from n=1, 2, 3, all the way to infinity. The band gap decreases, and most importantly, the exciton binding energy decreases. So now when we generate these charge carriers, they don't recombine. They can move around, and they're free from each other. So Ian Smith, in my group, crystallized the first n=3 lead-iodide perovskite. He formed single crystals of these materials. This is the crystal structure. And he decided to make a solar cell with this to investigate whether n=3 was thick enough to generate photocurrent in a solar cell device. I will give a brief description of Ian's work here, but Ian is giving his own talk today later on in the symposium. So he constructed a planar geometry solar cell device where he basically used titania, a flat layer of titania as the electron transport material, deposited the layered perovskite as the light absorber, and spun an organic hole transport material on top of that, and he found that this material does indeed work as a solar cell. Our first generation devices have power conversion efficiencies of about 4.7%. And this compared to the highest efficiencies with 3D perovskites, which have now reached about 18%, is a low number. But this is not an optimized device in any way. And I'd like to discuss some advantages of the 2D material with respect to the 3D structure. So for one, this has a larger band gap, so we can access higher voltages. These voltages are higher than any voltages that have been achieved with the 3D perovskite solar cell. These materials are layered. The structure is layered, and therefore they grow as plates. This is in contrast to 3D perovskites, which grow as cubes or blocks. And because of this layered structure, these materials love to form beautiful uniform films. So we can simply drop cast this material on a slide and this doesn't require any kind of high temperature annealing. We can form nice continuous films. And here I show you a film of the 2D perovskite, and in contrast, similar deposition techniques for the 3D material don't give the same nice surface coverage. And by far, I think the most important point here is that the 2D material is a lot more stable to moisture. So with the 3D material, here I show you powder XRD patterns, and over time, we see when this is exposed to about 50% humidity, we see the growth of new peaks, which completely dominate the spectrum after about 40 days. This is lead iodide, whereas in the 2D material, this material is pristine, untouched by lead iodide over 40 days. So we think that there might be a critical value of n, where we can make the inorganic layer just thick enough that it pretends it's a 3D material and has all the beautiful absorption properties of the 3D structure, while the organic functionalities can bring new functions into these materials. So you can imagine putting fluorocarbons here. This would look like you've taken your 3D material, sliced it, and coated those sheets with Teflon to improve the moisture stability at the atomic level. And we can imagine even molecules that absorb light or transport charge to bring new functionality to these materials. So with the rest of my time, I'm going to switch gears and talk to you about some very curious properties we've seen in mixed halide perovskites, in 3D perovskites. So here I show you again the band gap of these materials as you dope in bromide to the lead iodide lattice, and you see this nice increase in band gap energy as a function of bromide content into this lattice. And if we look at the photoluminescence spectrum of these materials, again, as we expect, we see that the energy of the emission goes to higher energies as we have more bromide in the material. This is exactly as we would expect, and we get this beautiful series. But Eric found that if he kept shining the light on these materials just at one sun illumination for just about a minute, this material changes dramatically. So he finds that as he keeps illuminating these materials, the initial photoluminescence starts to die down. And a new photoluminescence band starts to grow in that gets very high in intensity at around 1.7 eV. Curiously, it doesn't matter where the initial photoluminescence band begins, they all merge, and the eventual photoluminescence arises from this band at 1.7 eV. So the all bromide material does not show a shift in PL, the all iodide material does not shift, but every other intermediate stoichiometry changes and moves to this material that emits at 1.7 eV. And what's really surprising to me about this transformation is that it's reversible. When you turn off the light, you regenerate the initial material, and when you turn on the light, you get this new low energy PL, and you can cycle between this. Eric has done this several times. Here I show you data for 4 of these cycles. So we decided to study this material under illumination to figure out what on earth was going on. And we did several experiments. So here Eric sees that under illumination, a new sub-bandgap shoulder grows in at around 1.7 eV. And again, when the light is turned off, the shoulder decreases. Light is turned on, the shoulder grows in, and so on. This can be cycled. And Eric then wanted to study the structure of this material under illumination. So he decided to look at the X-ray powder diffraction pattern of these materials under illumination. So he employed this very sophisticated experimental setup where he suspended a bicycle lamp inside the diffractometer. And he just turned on this lamp, and this was enough to cause a change in the powder pattern of this material. When the light is turned on, he sees that every peak is split into 2 peaks. And when the light is turned off, he sees that the original peak grow back in. And these split peaks show the presence of a material with a larger lattice than the original, as well as a material with a smaller lattice than the original mixed halide perovskite. So we went to the electronic structure of this material to try and understand what might be going on here. And here I show you for the x equals 0.6 material, the valence band as well as the conduction band. When we hit this with light, there are holes in the valence band and electrons in your conduction band. We know that initially, the photoluminescence comes from these electrons falling from here to here, but in time, we get this low energy photoluminescence band, which means we're forming a trap. So here's my trap. We have some state where the holes fall into a state with lower energy. We know that the energy of this photoluminescence corresponds to the same energy as the photoluminescence from an x equals 0.2 material. So we asked the question, maybe why not form the x equals 0.2 material, but only under illumination? So our speculative mechanism can be summarized by this picture. We have this homogeneously mixed bromide iodide lattice, lead bromide iodide lattice, but when we shine light on this material, there's halide segregation that is initiated by the illumination. And here my darker blue squares show areas of higher iodide content, and these lighter blue squares show areas of lower iodide content. So there's halide segregation under illumination, and all the holes, of course, will move to the lower energy material, which is the iodide-rich material. And therefore, we get photoluminescence only from that trap. And our data so far support this speculation. If we were to fit this shoulder that we see emerge in the light-soaked material, that actually corresponds quite well to what we would expect from the absorption spectrum of the x equals 0.2 material if about 1% of that material converted. And if we were to form regions of high iodide content, that means we must, by necessity, form regions of low iodide content as well. And that also explains the split diffraction peaks, because here, this peak matches well with the x equals 0.2 material, and this peak matches quite well with the x equals 0.8 material. So halide segregation implies halide motion under illumination. And we know that this is a thermally activated process, because at different temperatures, we see different rates of this photoluminescence band growing in. And we can calculate an activation energy for this process. We get a number of about 2.3 eV. And this number fits very well with activation energies that have been attributed to halide migration in other metal halide perovskites. So just to end, I want to summarize this section. We see very interesting reversible changes in these materials upon illumination. So far, our observations are all consistent with halide migration initiated by stabilization of these holes through halide segregation. And we see this behavior even if you were to change the organic ions in this material. We see this behavior in films formed through all the deposition techniques mentioned in the literature for making these materials. We see this even in single crystals of the material. So we know it's inherent to the material and not due to any weird surface sites. And though I think this is incredibly cool, in terms of solar cells, this restricts the voltages that you can obtain from mixed halide perovskites. And if you really do want to form higher voltage perovskites, we need to either try to prevent halide segregation in these materials or look at alternative strategies to increasing the band gap. So for example, changing the metals or working with the lower dimensional 2D materials that I talked about previously. And I'm out of time, so I'll end there. I want to thank my group for the inordinate amount of hard work they put into their work. The students in my group and in Mike's group who have directly contributed to the GCEP efforts are listed here, but we often rely on the combined expertise of all members in both groups to move our work forward. And I'm very grateful for GCEP's support of this work that has really accelerated our collaboration. I'm done. Thanks for listening. I'm happy to answer questions.
Okay, do we have any questions for Hema? Bruce.
The result of the light-induced segregation is the first instance I've seen of a light-dependent solubility. So it seems as though the solubility is one number without light and another number with light. And so have you ever seen this before? And it can't be a kinetic effect because it goes back and forth. So
Yes.
You're changing somehow the thermodynamics of solution with the light.
Yes, I have seen cases of this previously where the migration was not reversible. So light-induced halide segregation has been noted in lead halides, in silver halides. When you use silver halides for photography, for example, you induce halide segregation in these materials, which are driven by the halide vacancies in the material. But I have not seen a reversible process up to now.
Very interesting data. Also relates to Bruce's question. So light comes in, and then these halides start to move around and segregate. So do they come out of crystals and then go into the environment? Would that be a degradation mechanism? So iodide certainly is well known. Light comes in and then split it, and then
Yes.
iodide goes away. You know.
Yes, we have fooled around with a few of those experiments. So for example, if you take this material and disperse it in hexanes, and over time, if you irradiate this material and you do a starch test in the hexane solution, you see iodine. So the halide will eventually leave as X dot, and two X dots will get together and form the halogen. Those are extreme cases where we basically try to decompose the material. In these materials, because we see such beautiful reversibility, I don't think the halide will leave the material.
The stability issue under moisture, have you checked that out to see how, is it worse when there's light present or not? I think all of your stuff was done in the dark.
Yeah, actually, we haven't considered the effect of light for the stability test. We just use these controlled humidity chambers. That's an interesting point. We should do this in the dark and in the light. We haven't noticed any differences that really stand out for now.
Well, if there are no more questions, let's thank him again.